Okay, hello everyone. And let's see, this sounds kind of strange. Let's see if I can get my audio levels once more in a working order. Hey Tutu, welcome back. Echo. Oh, is there an echo? I don't hear an echo. Oh, yeah. Oh. Okay, so there's no echo on my side then, I take it. But that would explain it, yes. All good. Thank you for the report. Can you guys hear the music all right? And or why didn't you hear echo on the music then? Yeah. This kind of looks... Everything seems to be pretty okay here on my side. It does sound a little strange. Maybe it's just... It's perfect. Excellent. Excellent. Let's go with this and do let me know if it turns out to not be great after all. So, welcome everyone. And welcome back for some more Traction Point development. This is indeed sort of a ninja stream. Oh, this wants to update. Yeah, let's just let it do that. This is indeed sort of a ninja stream. It's kind of the only kind of stream I can do right now, if I'm being completely honest. Because with my kind of life situation and work situation and everything, I don't really have the option to schedule these things all that well in advance. Let's see if we can get the proper solution running here. So I'm afraid you're gonna have to deal with ninja streams, because it's mostly like I realize maybe like an hour before, half an hour before, sometimes 5 minutes before the stream, I realize that, yeah, actually I have a couple of hours, and so I just do a little bit of streaming. If I was trying to stick to some stream schedule, I would just disappoint you guys, so I'm not even gonna try to do that. But let's see if we can run the game here. Let's get rid of the in-game music for today. We're gonna do a little bit of particle effect work today, as I'm sure you have seen there from the stream title. Basically, I'm going to be super crazy busy for the next 5 or so days. So there won't be any streams probably until next week. But I have this one little task that I've been meaning to do for a long time now, actually. And I figured, yeah, let's just see if we can get that done on stream. It hasn't been planned all that well, so we'll see what kind of disaster this turns into. But we'll try to get it done. Basically, we're talking about these flashes here. You can see it's kind of fake, actually. It's just a billboard. There's not even any like actual light in the scene. It's just a billboard that's placed on top of these guys, and they kind of blink away. They blink away like this. I think there's one also on top of this mast here. And these are the only, or this, shall we say, this particular effect is the only so-called old style particle effect that I have in the game at all these days. So some of you might know that I have essentially 2 particle systems currently in the game. I have the one that's just called the particle systems, which is the old one, And then I have the new node-based particle systems called the Merlin effects. And all this like low poly dust here after the car and all of that. All of this is Merlin particle effects. Basically, I've just had that one red flare thing there, which has worked well enough, but it's kind of silly to drive the whole old style particle engine for a simple little flare when I'm not gonna do a whole lot of new effects with that system. So I figured let's just port that over to Merlin today and see if we can essentially like not remove the old system, because I still use it in some of my other projects, but it can basically be dormant in this game, which should potentially free up some resources and things like that. Kind of doesn't make any sense to have it running there. I have been doing like a whole bunch of optimizations in the renderer mostly for the past 3 or so days. This demo scene runs like 99% of the time now at 60 frames per second on the Steam Deck. I'm not super happy with it yet. I like it to be a solid 60 frames per second, which you basically can't break from. But unfortunately, we're not quite there yet. But like I said, like 99% of the time we're at 60. So I think it's already basically shippable performance. But we'll see. I'll see if I can come up with some other clever little hacks. I'm telling you this because there's a real possibility that we'll run into some like graphical glitches or new bugs here, because yeah, I've done a whole bunch of new things. In the meantime, or shall we say as a result of this, as byproduct of this, I've also fixed some bugs that we had previously. So there are actually some glitches that have gone away, and some things that are just like better tweaked now, things like draw distances and whatnot. So there should be a lot less pop-in, for example. So that's kind of neat. But yeah, we'll see where this ends up and what we run into. But let's get going with these particle effects. And basically how this works is that these pillars here are made up of just like a whole bunch of different objects like this. We talked about this on a previous stream, that these are now kind of made up of individual pieces, so we can just add more things to these pillars here and have them kind of be made up of a kit, essentially. And what I have done here is basically I've just colored the top of this red like an actual light, and then I placed a particle system on it like this. It's completely like separated from the pillar itself. I might later actually put in like a light here, which we could do already. Let's see. So we could put in like a point light here. Of course, this point light, it would not actually be flashing like this, right? Because its radius is like super large. It would probably be something like 2. Yeah, there you can sort of see the effect of the light there. And we could make it red, red like this. But of course we would have to control it somehow to actually make it sort of turn on and off with this. It's not really very visible currently. If we turn off the sunlight here, we might have a bit more of it. But anyway, basically why I'm telling you this is just that this is sort of like a very fake kind of flare. Doesn't really light anything up. It's just a graphical particle system object that I've placed at the top of this mast here. And basically, rather than having these things, we would replace it with a Merlin effect. And we have something called a placed Merlin effect. So let's just move this guy out of the way for a little bit. Actually, before we do that, I'm going to copy its transform. I'm going to place here on tower number 2. What happened? Oh no. Yeah, it didn't like that for some reason. Okay. Like I said, might run into all kinds of things. Let's see. Refinery. I'm gonna attach this to the process here in case we actually kill ourselves again. Attach. Oopsie, yeah. Oopsie indeed. Let's see what's going on here. Particle system. Copy that one. Move it off to the side. Have a placed. Make that the active parent. Place a thing there and move it there. And there we go. Now it's fine. Yeah, I don't know what happened there. That was weird. Yeah, it's still rendering the light probe, so it's a little slow. There we go. That's better. So now we can basically we can give it an effect path, and we need to give it yeah, it doesn't have its own you know, set of resources, these Merlin effects, but we can find them basically by filtering for bin MRL effect. And so here, for example, if we wanted a fire at the top of this thing, we could have a fire there. Ooh. Now the thing is on fire. Isn't that cool? That looks pretty funky. So you know, in the level, this looks kind of similar in a sense. This placed Merlin effect type is very sort of very basic. It doesn't really give you, it just gives you the option to whether or not to auto start it and whether or not to let the particle effect finish if the parent dies. So if the game object is deleted, should we let the particle effect finish? Well, this one actually never finishes because it's a continuous one. Yeah, so if we delete that, you can see it dies immediately. I think if we delete it now, yeah, now we can sort of see it sort of like stops emitting, but it finishes. Of course, there's like a whole bunch of various like parameters and things that you can set on these guys, which is how we can attach them to things. And we could attach a Merlin particle effect directly to this tower, for example, but I don't think we necessarily need to do that. Let's have a look here. I think this is a Zig component, so let's do placed. Now, what is it called? Placed Merlin effect is the object type, but this is just effect component. Effect component. Yes, we have attached effect component, and then we have effect component. Let's see. Hey, just joined. Why is the speaker burning? I mean, why not? It's a pretty rock and roll burn, I think. Can we actually scale this up? Does it work? I don't think it works. No, we can scale up the object. You can see the object being scaled there, but the actual effect doesn't scale. Let's see. It looks good. I thought it was convolution bloom. No, it's not convolution bloom. It's just a very basic additive blending bloom effect. This is actually not a very good. This is not a very good fire particle. I think. I think I had a cooler one actually. Let's see. That's a prop bundle. Okay. Bin MRL. Yeah. Some of these might actually be broken, so I don't know. But yeah, we can add the smoke pillar here as well. now the pillar is smoking. We need to, it's offset a little bit from the actual place. Now we have now we have the smoke from the actual speaker there. Oh, it's offset that way as well. I think this one obviously goes like on top of this fallen. Let's see if we can actually find it here. Smokestacks. Smoke pillar is right here. Smoke pillar effect. Yeah, so there we go. It goes there actually, and it's sort of modeled specifically for this place. So you see it go kind of around this, and so its pivot is down there, but it actually smoking through that roof hole there. So that's why it kind of like looks very strange. Hey Volodymyr, welcome back. Anyway, this is just me being silly now. But to give you an idea of how we kind of hook into the system, you can do things like this. We have the cartoon smoke continuous, which actually, yeah, it's very, very subtle if you don't actually start messing with its parameters. So this is the smoke that is actually spawned off the tires, right? And then we have, what do we have? Bin MRL. We have some like strange looking like flow what is it called? I don't remember actually. What is it called? What is that thing called? Rotating thingamajig. Let's open it up in the editor and have a look. There's a node here which drives that whole motion. It is called I don't remember. Why don't I remember? I think it's this one, isn't it? Let's connect the game. It's not Boyd's. No, it's not Boyd's. It is. It's basically like a flow field. Emit particles at particle scale, particle velocity. Oh, curl noise. Curl noise is what I'm looking for. Yes, this one. This thing here. Yeah, you can see the seed here, and it creates like a different looking effect. So this is kind of interesting. It makes these kind of like, yeah, like if you plot out the curl noise, it almost looks like, you know, like a topography on a map or something like that, because it makes these kind of like curling lines like this, and then you can have things actually like follow them around. Unreal Engine 4, I think, is the engine that like made particle systems using curl noise popular. It's a pretty interesting thing, but it's of course like it's noise, so it's randomized. It just makes makes it look kind of funky. Curl noise, yes. Exactly. Yeah, it looks pretty intimidating. Blur. Anyway, yeah, I have a lot of like these things were obviously just like tests for Merlin when I made this system. I haven't done like a whole lot of particle effects. I'm not a very good technical artist, so these are just like different colored different colored diamonds or whatever, isospheres basically. But yeah, anyway, let's undo all of that. Chip, chip, chip. We're back to where we were. And I'm gonna get rid of that as well. I'm gonna look at the old this particle effect here. This is very simple flashing. So what I was thinking we would do is we're gonna port this to Nemo. Shouldn't be very difficult. And then we are going to look and see if we can have it running as native code. So in Merlin, we can see here that okay, for this particular effect, native code generation fails. I'm going to press F12 here and see why that is. Well, we have an error. Node code generation method defined for the type curl noise node. So if we want to compile these effects to native code, which we generally want to do, because that makes them very, very fast to execute, because these are execution graphs, then all of the nodes in the particle system need to support native code generation. Native code generation is something it's kind of like a work in progress still. So this monster of an effect which creates this big smoke pillar. This is the effect that kind of prompted me to make native code generation work in the first place. So this is the big one, and you can see it has like a bunch of things. It has these like embers flying around here, and it has these two kind of large smoke pillars which follow these curves that drive this. Hey, Xluxy, welcome back. And what this does, if we look at the source generation here, it actually produces a bunch of GPU. Sorry, I'm reading the question here. Yeah, I'm gonna answer your GPU question a bit. This produces a bunch of code. This is Git. You can see it's pretty long. It's like 7,000 lines, but a lot of it is just like these very long lists that essentially get like, you know, collapsed down to almost nothing. We also have a bunch of, look at this, JSON curve path nodes. So we have a bunch of like inline data here in this for like lookup tables and things like that. All of this is compiled down into native code, which means that we can run a pretty complex effect like this in, you know, we're talking like microseconds here. Normally this runs in interpreted mode, and this, for example, here is completely interpreted, and that's why that's because this code generation here is kind of like, it's not really a finalized thing yet. I need to basically copy paste this code out into another project and then build that project by hand. But I was thinking we would, once we have that blinking thing working on the top of the pillar, if it doesn't actually generate native code for it, we might go ahead and actually implement those nodes so we can get it working as native code. And yes, to answer Vladimir's question, I have considered doing GPU compute shader particles, yes. The thing though is that when I was, and I think I've answered this a number of times previously, this exact question, and the reason it works on the CPU, the simulation right now, is that I had this node framework working already for things like sound effects and mission scripting, and I basically wanted to see if I can make it work on or for particle effects as well, and that's how this entire Merlin application came about. And this thing now runs on the CPU. And then when I inevitably decided that, okay, I need to run a little bit faster, I made it so that it can generate native code. Now the next step, when we have this thing working, is exactly what you say. We would have it generate GPU code instead of CPU code, which could be very interesting. And actually, certain people have used Zig as a shading language for generating things like SPIR-V, for example. So it is something that, you know, potentially could be even run on the GPU. I'm sure it would require some small changes to this code though, but a lot of it is actually really kind of simple. So there's like, if we really go into like the nitty-gritty of how this node graph is executed, there are certain things in here which might require a little bit of re-engineering if we wanted to run them on the GPU. Like for example here, if we look at, like, we have the effect starts here in on start, and then it starts a bunch of repeating actions, or two, shall we say here. It also jumps to the other sections like sparks and things like that, but we have just these two sections here. So what actually happens here is that we fire off a connection to this repeat node, and then this repeat node starts repeating this action here, like just fires this action node, and it gets the period here dynamically through this, which returns like from 0.9 to 1.1 seconds, so roughly a second. Roughly every second we spawn a new particle, and that means that we have essentially multiple places of this node graph executing simultaneously, right? And this one, for example, here, it just keeps repeating this action node, firing this off until someone calls stop, like enters through here. So basically we never stop this thing, right? At the same time that is happening, we do other things here. So for example, here we have the entire like particle update chain. So you can see the execution pin color changes from just a standard gray here into this particle category purple, and that means that this particle update that happens here between these pins here, this is updating within like a particle context. So that's why we can do things like, you know, store particle value, set particle color, set particle scale, set particle position. We don't need to tell these nodes, hey, which particle are you actually operating on? We could just tell it set particle scale, and it will figure out, you know, which particle it is running in. If the particle dies, rather than firing update here, it fires death. And you can see here we're essentially back to just a normal execution flow. So there's actually quite a lot of, like, you know, quite a few different levels to executing a node graph like this. And I'm not sure it would be, first of all, possible. It probably would, but second of all, very, you know, wise or a good idea to do GPU particles in this way. Like, GPUs just want to, like, chew through lots and lots and lots of different set of like homogeneous data, essentially. So I think what I probably should do if I wanted to make this run on the GPU is that I would have this part, this purple chain, which starts here and then basically goes all the way over here to that one, and we have a separate one here which goes all the way to that one, and so on. I would have these chains run on the GPU, and then I would have the rest of the, like, the repeating logic and all of this would run on the CPU. That's my thinking, but I haven't done it, so I don't exactly know. But if we look at the actual, like, generated code, there's something called a kernel, just down here, all the way down here. It's actually, this is already the kernel. Kernel is right, starts here. Here's the kernel. the kernel has, and this is a struct, it's just like Zig, basically. It doesn't have namespaces, it has structs. And so in this kernel we have a whole bunch of nodes. Here are all the nodes. And then it sends data between these nodes. And here in this hard-coded natively compiled version of this, we can actually follow the logic pretty well here. We can see that, like, okay, repeat node 5, so it's the repeat node. If we look for that repeat node 5, we have it here. Here's repeat node 5. Repeat node 5 reads its period from node 46. So we can actually see that we should probably be finding node 46 here. Yeah, there we go. Get period is just hard-coded to get it from the kernel. Node 46 get result. So I'm pretty happy with the performance already of this CPU version when compiled to native code. But if this doesn't actually pan out, then it would definitely be something to look at to actually get it working. But if we have a float here, this would now be getting the node ID 232, and if we put, like, I don't know, 123 here, and we plug this into that one. Oh, we don't have. Okay, yeah. This is one of the things that I spoke about earlier. All of the nodes need to have their node gen or code gen set up explicitly, and evidently I haven't used any float node, any just like pure float nodes in this. Yeah, so we don't have code gen. But basically, what this could do now, when we are generating the code, is that, like, we could just inline this value 123 directly here in this repeat node, because we can see that this gets its period all the time. It gets its period from this node, and it all the time, like, statically, one might say, returns the value 123. So we could just, like, inline the value 123 here. And of course the Zig compiler is very good at just, like, eliminating paths that never change. So it should be pretty good. And the interpreter, so the thing that actually runs all of this code now here, because we're not compiling any native code here, right? We can make changes to this, for example. Just make that, like, spawn something much less often. You can see that immediately it changes the shape of the effect there. So this is now interpreted from this node graph. And it also does, like, static value caching as of about a week ago or so. So yeah, it should be pretty good. Jesus, this is complicated. Yeah. Well, it's not very complicated. It's not very complicated. Like, the runtime which runs this stuff is probably less than 2,000 lines of code or something like that. Actually, it's like, if we're looking at the interpreter, which is in C++, the native code is in Zig. If you look at the interpreter, it's basically like node graph H is like 118 lines. Node graph CPP is 529, and then we have the execution context, which is like 190 plus 276. Yeah, we're not even at like 1,000 lines of code here for the core, right? And then we need the actual code for the nodes themselves, and that varies, of course, right? So if we have like float node, for example, float node, it's 40 lines. It basically has just a pin value function that reads the node and writes it to a value receiver, a pin value receiver, which is the one of these guys. Yeah, and we don't actually support native code gen for that node, so we can't really look at that. But like you can immediately see here what like the node 5. I need to go to it here. Yeah, here's node 5. Some of these are kind of complicated. Like here's all of node 5. It's pretty long actually, all of that, because it needs to do a whole bunch of like bookkeeping. So that here's the update logic itself, and it keeps track of like, okay, so are we repeating, and are we updating the repeating, or are we stopping, and is the initiating cursor the same as, or actually this just checks if it's an invalid one. But like you can do some crazy things with this. You can do things like copy this and then put that back there, and then you like plug that back into stop and things like that, and it needs to handle all of that like gracefully. So for what is the resource path hash? What? What's the where? What? You need to give me some more context here. But here actually, yeah, here this is a new thing. This was added last week actually. I went down a little bit of a rabbit hole in optimizing the interpreter for these guys, and they just got like a whole bunch faster. Like a float node, for example, which looks like like this. Blips. You plug that in there, for example, and then you write 666 number of the beast. If this node now wants to know the angle, and it plugs it into this float node here and returns this value, we know that this value is never going to change because this float node always returns the same value. So then this float node actually returns static here, and that means that if this is static and this also is static, we can plug it into the same thing actually, and then we make like a like a vector node here, bloops, like this. Then all of these three are static. That means that the output of this is also static, and then like you can eliminate entire branches of the node graph with this, which like depending on your graph can make it like it can be like an infinitely faster. It can make it like 10,000 times faster than it was, or something like that. But if everything is dynamic, then of course that doesn't help. Let's see, in the code gen on the top, resource path. Okay, right. Yeah, we need to undo some of these changes here that we made. Yes, okay. So these two guys here. This is something I was thinking of coming back to when we actually, start doing some work in this stream. So the generated code for one of these effects include all of the nodes. So here we have node 0, node 2. Apparently I've had node 1, but I've deleted it, so it leaves holes. Node 2, node 3, node 4, and so on. And then at the bottom we have the kernel, which we looked at, which has all of those nodes. Here's the kernel. You need to basically take all of this code and you need to put it somewhere. And on Windows, I could, like, in theory, I could build all of the effects into their own DLL file, because Windows doesn't really have a limit on how many DLL files you can load from a process. But That's not the case on other platforms, like Linux and Mac OS, for example, has to my understanding, very real limits on how many DLL files you can actually technically load. And so I don't want to limit myself to that, even though it's kind of like probably several hundred, but still, you don't necessarily want to limit yourself to that. And because of that, I actually plan to have it automatically bundle all of the natively compiled effects into a single DLL file. It doesn't do that currently though, because it doesn't do anything automatically currently. And so instead what I have here is a solution which handles, it's called Sprinter Native. Sprinter of course is the interpreter and overall like node execution framework that we have. And so anything that's like natively compiled Sprinter stuff goes in here. And here we have Merlin native. Merlin of course being this this particle business. So here we have now, these are all my hand generated effects that I'm basically testing out in their compiled form. So here we have this pretty massive effect we just looked at. And here we can see that, okay, it doesn't have a resource path here because like the editor doesn't, either it doesn't know it, I don't exactly remember, or I just haven't written the logic to figure that out yet. But basically all of the natively compiled effects, they need a resource path, because in game you're requesting these guys by resource path, right? So if you go to this one again here, smoke pillar effect. Smoke pillar effect has a path here, right? This is the path. Game/Merlin effect/refinery smoke pillar detailed bin MRL effect. There's the resource path. And so the DLL needs to know, hey, I have native implementations for all of these effects. So if any of them are requested by the game, I can just provide them with a fully inlined natively compiled node graph. And the idea is that this would be generated automatically, but it doesn't do it yet. So here if we go and have a look at the top of this file, we can see that it has the path here. And the path hash is just a, I don't even know, is this actually used? Yeah, it is. It is actually used. I think this is the the thing that is in fact used, and the path isn't. But the path hash is just a, it's just a hash. It's a string hash of the path, really. So the detailed one, yeah, it's this one, node graph 5. It's probably the last one that I had actually working because it's the most complicated one. But yeah, you can see that we import the smoke pillar detailed, and it provides a resource path and a resource path hash, and you can just like, hash node graph. This is exactly what I was just talking about. If the game tries to load a particular effect, and we have a natively compiled DLL available, the game, or the Merlin runtime rather, asks the DLL, hey, do you have this effect? And then it just checks, yeah, we have graph 5, true. So it's just very simple. You can see that this code is not very elegant. It's very sort of there's a lot of repetition here, but my thinking is that this part, as this comment says here, this would all be generated when I eventually make the little shim which actually write this code out. So a lot of lists, and then generated section ends, and then we have some handwritten stuff, so to speak, after this. That's not very long, it's like 194. But the idea is that like between this end tag and this beginning tag here, the resource packer would just run through all of the nodes, see which one it can actually compile to native code, and then add a Zig file here in the generated folder, include it here, because the generated section begins, generated section ends. Include it here and keep track of which one is which, right? And then it would add them to this list. That's it. So yeah, that's why it's that way. So if we start working on this red flare thing today, it would be node graph number 6 and it would go in this list, and then that should basically like just work. And of course the node or the red flare here in the level is actually super cheap. It's not something that we really need to make natively compiled, but it's a pretty good idea to try to make this work, because sooner or later I'm gonna want to do all of this native stuff automatically anyway. So that's what that is. But hey, let's have a look at the old system now. So we have this particle system here, and this also has a path. It is called game/particle system/testing red light flare bin particle. So if we look at this, it actually goes to basis particle. Basis particle is the sort of like work format. You can see this is the old particle system. This thing hasn't seen any updates in probably, I don't know, 6-7 years or something like this. Haven't really expanded on this old style particle system at all. And there's not even a preview here, but I think what you can do, shut down this for a little bit. We don't need that. Let's shut down Merlin, because we're working with the old one currently. So if we go here and we look at red light flare, yeah. What we can do here is actually we can click preview here, and we should see it in the preview, and we do. Isn't that cool? So now we can actually use this here to, you know, if you change the color to green, for example, and then we need to actually save it. Look at that, now it's green. Isn't that cool? We have 2 emissions here. I wonder why do we have the 2 emissions? Okay, we have like a... We have a red dark and a red light. So we have like particles, and you can see this list here is like what the particle has. How the particle behaves, how long it lives, how it moves, how it scales, all of that. And then we have emissions. We have 2 emissions, and each emission targets like a different particle. So if we disable that one, what does the other one actually look like? Okay, so it looks like that. It's just like a... It's like a slightly smaller and much brighter. Let me just revert that. Yes, thank you. It should be back to its red one. Yes. So if we... I was actually thinking it had just 1 emission, but evidently it has 2. That's interesting. You can see there's some like... there's some weird stuff going on. You can clearly see like boxes around that. I wonder if that's a shading bug or if the texture is just kind of wonky. But anyway, we're gonna use the exact same texture today. So if we use it without the brighter one, yeah, it's just... It looks kind of bad, actually. It clearly requires, you know, both of them to look good. Okay, that's cool. We can definitely represent that in Merlin as well. So what do we actually have here? If we open this up, this should be just JSON. JSON data. Yes, just JSON data. So let's actually go and compare these two to see how they differ, so we know what we're dealing with. I'm going to open Beyond Compare here. It's just to make it easier to see, like, okay, what do we need to do to actually like replicate this effect in Merlin in a little bit. Goes all the way to there, and then we have the emission definitions. That's much shorter. So basically, the only thing that differ is the name, the color, and the scale. Everything else is completely the same. So yeah, it's just slightly smaller and it's brighter and it has a different name, which of course doesn't really matter outside of the editor. So we can see the scale multiplier. It has a curve. No, it's okay. It's here, is it? Where's the scale? Right. Okay. So it doesn't really have a curve. It has just a single point. The single point here. This might be a little weird to look at in YouTube, I guess. And you know, as of some Windows updates ago, the icons in this this curve editor are completely broken. You can see they look really bad. I should fix that. But anyway, it has just a single point at 5, and this one has a single point at 3. Scale is here. Yeah, this one is at 3. But of course, we could have, you know, more of these. So this goes from 0 to 1. So we could make it, you know, put another one there, and make that sit at 1. And now if we save this, the like smaller one should scale up, I guess. Oh, but it's just so very, very subtle. Let's make that like, I don't know, 1. So now I can see it. I can clearly see that the brighter one being like scaling up a little bit. Which, you know, doesn't look very bad, but I'm not sure that's what we want to go with here. But you can do things like that. Anyway, I don't think there's like a whole lot of interesting things going on in this effect. Let's look at the red dark one again. So it has it's a billboard particle. Emitter type is point, so it's spawned at the exact center of the particle system. We could also have a sphere and a box. Blend mode is additive. We don't sort anything because we have basically one at a time. We have a texture path and we have a shader path. That's not how Merlin particles work. In Merlin we have proper materials, but then of course the material sets up the texture path and the shader path, so so we get it through that. Lifetime, min-max, that's fine, we can do that with Merlin. Then we have 3 colors here, and the color, we can blend between the colors using a curve. Again, we can see that it's just sitting at 0, so it basically selects this first color here. And opacity, right, so this is kind of like the only interesting thing here. Over the course of the particle's lifetime, the opacity goes down, and that's kind of how it like fades away essentially. So it starts at 1, and the x-axis goes from 0 to 1, starts at 1 and goes down to 0. And it has no velocity, and the scale, as we saw, is set at 5 and 3 respectively. We don't do any rotation, so that probably sits at like, is it 0 or is it 1? I don't remember. Yeah, it's just 0. No gravity, No velocity drag. You know, we could have one of these be like 10. Now the darker red should start going down a little bit. Can't really be seen. Does it actually work? Yep, it does work. Oh, it goes up, of course. Yeah. Minus 50 or something. So you can see that we can actually do quite a few things here with the old one as well, but it's just kind of like more limited. With Merlin, you can like have essentially arbitrary complex node graphs, driving everything from like lifetime to scale to movement to everything. But okay, once again, I'm gonna revert this, and we will basically just start and see what we can do in Merlin. So I should have some suitable materials already set up for this. Let's have a look here in means data. Let's see. BB particle additive base material. So BB stands for billboard, which is what we are going to want to have. We have an additive one, and we have an alpha one. And then we have additive 32 and alpha 32. I don't know what that is. Let's see which one we want here actually. So this is of course like a completely standard shader essentially, right? How's this set up actually? We actually even have like shadow maps and things here. Okay, we don't want that. Not for a flare like that. But what we do here is we have a texture, we sample it, we have a bloom amount, and then we combine the texture value with the bloom amount. Set that as the bloom color. Set the color from the. Oh yeah, we have a color here actually, which we are probably reading from some suitable Merlin place. So we can have a texture which is black and white, and I bet actually that texture is black and white that this red light flare is using. What is it called? It's called FX Flare 1. Let's see what that actually looks like. FX Flare 1. Yeah, it looks like this. So then we color it from the node graph. And I think actually vertex here is probably in some ways the more interesting one. It has a Merlin billboard particle VS. So this does something special that Merlin expects it to do. Here's the actual shader code for that. Yeah, there's some sort of unpacking of math here that Merlin puts in certain places. The Merlin billboard particle render stores the transform values of the particle in somewhat non-standard way, and then it kind of like unwraps that and passes it to us. From this, we have the position, we have the color, and we have the UVs. And then you can have just a standard pixel shader hooked up to that. So that's how the billboard materials work. What I'm not fully aware of now is like how does this additive base compare to what? That's not what I wanted to do. Go away. this guy, how does that compare to this guy? Oh, okay. Yeah, this is a variant. Yeah, that's a variant. So if we open this additive 32, it will open the base material here in the back, BB particle base material. That's the one we just looked at. And then it fills in some values for us. So here in the base material we have a texture which falls back to the fallback diffuse texture, so you kind of don't want to use this. But this one actually does a round and rectangle 32, and then it has no bloom. Okay, cool. So it's just like you want to use this, which is based on this, and again we want to make a new particle material essentially for this one, based on the base material, and we probably want to put it somewhere. Where should I put it actually? Let's make a new folder here, and we call this just like static props, or I don't know, miscellaneous. You know, a red flare can be used in a whole bunch of different places. Red light flare. So let's create a new particle effect there. Gonna get rid of that, and I'm gonna save this immediately here. So miscellaneous red light flare. Let's hope I remember how to do this now. So maybe we'll start by adding that material. I'm gonna take additive base material here, and I'm gonna create a variant of it. And for the texture, we're gonna use that FX flare number 1. And then we'll save that variant. Merlin effects, miscellaneous red light flare, like this. And we can even export it. And it exported successfully. That's cool. So now we should have a bin material here, red light flare bin material. And now then, if we think about this, how does this actually work? So we have effect. This should have an on start node, and then we can have the repeating logic once again. So repeat, plug that into there. If I can manage to hit it. And I think if we look at the old one, they have a lifetime of 1.3 seconds. So that means that we want to spawn a particle at an interval that is larger than this, right? Because it kind of blinks and then it goes away and then it blinks again. That's how the old particle system works. So you can see here that we have two emissions. They both have the same start and end time. So they start at 0. Basically, that means that they immediately start spawning or emitting, and they end at 3 seconds. And then it kind of goes back to the beginning. But of course, because the particle's lifetime is just 1.3, that means that there will be 1.7 seconds of no particle after that, and then it goes back. So every 3 seconds, essentially. So let's put that to 3. And then we can emit a particle. Emit particle right here. And it is set to point. That's fine because we have the emitter shape set to point here as well. We have the same sphere and box here. If you have a sphere, it spawns at some radius from the from the transform of the effect essentially, and box you can get to set a size there, but we don't need that. We just have a point. Lifetime was set to 1.3 essentially, so that matches this stuff here. Then we need a renderer, and this is now a billboard particle renderer. Let's plug that in there. Material resource path is basically this one, red light flare. I don't think it's gonna show it to us here, because no, if we restart this program now, because I added that material after starting this. Now if we type red light flare here, it should give it to us, red light flare, like so. That's cool. So okay, now we are spawning a particle every 1.3 seconds. No, sorry, every 3 seconds with a lifetime of 1.3. But then we have a particle that kind of comes out of this, and we don't do anything with it yet. So that's not good. I think the only thing that we need to actually have this show us something is that we need to update the particle. We need to have an update particle node here, which kind of like, you know, drives this particle. And every time it dies, it fires this one. And for every update, it fires this one, which is, you know, we can plug any kind of modification to the particle into this update pin. Let's just, for shits and giggles, add a format print here to the death. Particle died. Oh, that's not how you write died. Particle died. So now if we play this, look at that. Beautiful. So it stays visible for 1.3 seconds, and then it stays hidden for 1.7 seconds. And the particle dieds, they get printed here to this asset browser output. So that looks all right, I guess. We need to set the color of it. First of all, set particle color. Can drag one of these guys here. And the update for the particle can be thought of as basically consisting of two different steps. Everything starts with an emit particle node. And then you can have any number of particle nodes in between the emit particle node and the update particle node. And these guys are executed once. So what happens when you emit a particle is that you enter through here, and then it runs the sort of initial setup of the particle, which comes out of this particle pin here. And then you can hook up a bunch of like velocity and scale and whatnot particle nodes from here, and then it enters this update particle node. And then as long as the particle is alive, it fires this once per frame. So this is again, this is like the setup node. This should make it very, very red. And there it is, very, very red. All of its glory. I'm a bit bothered by this border here, which you can see. It's kind of faint. I'm not sure if it shows on YouTube. It is of course not Merlin's fault. It was there in the old editor as well, but it's a little annoying that it's there. We might have to look at that at some point. Let's look at the actual. What is the color that this? Yeah, it is like 100% red. This darker one. Okay, red dark. Okay then. Can make it here red dark. This is the red dark path. Actually, we want the same red light flare material for both of them. Then we want a scale, so we'll set particle scale, and we want to mimic the previous one. So this would be 5, and it gets a bit larger. Cool. And I think the only thing we want to do now is we want to set the opacity, don't we? Isn't that how it actually works? Set the opacity here. Do we have an opacity? No, but we have a color. This is alpha blended though, so yeah, I think the alpha channel should still work, shouldn't it? I'm sort of thinking it should. So if we plug this in, and now we're after the update particle, so here we can make you know, small changes. If we preview this, it should go back to white because we're setting it to white here. But of course we can just, like, you know, do something funky. Vector node. Random float. Random float. Okay, yeah, we need to set that to 1. Hey, look at that. It's a flashing thing. It's kind of annoying, so let's not do that. But you get the point. Let's do a curve. And we need a color here. So again, let's do actually a vector. Thank you very much. Vector. And since we basically only want to adjust the W component, we want these guys to be the same as previously. I'm thinking we'll probably just do a color vector here. We set this to red, so that would be 25500, right? As red as can be. And then we plug that in there. And then we do a vector decompose. We plug all of this here. So if we want to change the color later on, we can do it all from this one place here. Something like this. Plug that there. Sure, put it 0.5. Let's just see that it actually works. Inputs on a curve node. Okay, yeah. It's unhappy with me. Yeah, so now it does work. It's like a slightly fainter one. Now it's back to what it used to be. That's fine. If we add the curve back here though, and we plug the curve in here, now we can drive this over time. And we're gonna need a particle get particle data node, which is right here. You can see this guy gives us all kinds of things. And what we want here is the normalized age. The normalized age runs from 0 to 1 over the course of the particle's life. We also have absolute age. We have like positions in world and local space. We have rotations, we have scales, and so on. But let's get the normalized age and plug that in here. Right? And then, like I said, the kind of only interesting thing here in this old one is the opacity curve, which looks something like that. So it's kind of like an S-curve. I should probably just have a node for an S curve here, but I'm gonna do my best to approximate it. So plonk and plonk. We have that at 0. No, we have that at 1 and 0, and we have this one at 0 and 1. Ain't that how it is? And then we can take this and we can do smooth. No. Okay, yeah, it probably doesn't actually work now that we have like actually pointed those things at each other. So I'm just gonna manually bring it down like this. So here we have our beautiful curve, and it looks kind of similar to what this was previously. So okay, that's nice, thank you. Okay, does that look like the old one? Oh yeah, they use the same UDP port, those two guys. Ah, and this guy doesn't like it when they do. Yeah, yeah. This Merlin preview is kind of mimicking the asset browser, if you will, asset browser preview. It kind of just pretends to be an asset browser preview so that I can reuse a lot of the code, but they're currently set to use the same UDP port. I should change that. It doesn't matter though, we can look at it here in the editor instead. So that's the fade that's happening there. And of course we don't have this like brighter center that we have going here. We're gonna add that back in a second. But let's maybe detach this preview from the Merlin. And then we can see here, do they look the same? Yeah, I think they're pretty good. Yeah, this thing, we can disable the sleeping there so it keeps actually showing us the effect. Okay, that's pretty nice. So let's add this brighter center to this guy. That should be very simple. And it can be done in a couple of ways. Since the only thing that is actually changing here is the scale and the color, we could potentially like store the let's see, particle branch is right here, right? Like the easiest way to do this is basically copy pasting this chain, actually all of that, right? And then paste it down here and then make this red. Was it light or bright? Red light, yeah. And then we hook that to there. And we can reuse this curve, so that's completely fine. Just put that there somewhere. Like so, and then we copy the this color. What is that? 245167. 245167. 167. There's the other color. And then this would be 3. Right? That doesn't look correct. Oh, I know what the problem is. We haven't connected the renderer. There we go. Ah, there's our old friend back. That looks pretty spot on, I think. So this is actually this is the easiest way. And look at this. Look at this. Native code generation succeeded. So here's the code for this particular effect. Like before, we don't have the resource path yet, but we can figure that out. That's not a problem. So we have an on start node, we have a repeat node, we have an emit particle node, And yeah, you can see some of these nodes have a little bit more code, but it's not that bad. Billboard particle renderer node. And then this is one of the most complicated nodes here, I bet, the update particle node, because this handles like, you know, update transforms, fire and update the out pin, update the particle's age, and check if it has died. So, you know, if a particle dies, we just have an if statement here, and then we exit through the death pin. Set particle color node, set particle scale node, another particle color node, curve node, a vector, another color. Pretty basic stuff. Vector decompose. And all of that. And then at the bottom we have the kernel, which basically like dispatches update calls to these guys. So if you have an update function here, for example, it just checks, okay, what's the current node ID? And then it just like dispatches calls to them. Like this. So pretty simple stuff. The annoying thing here, of course, is the fact that we have like a lot of repetition here. So I'm wondering if we can make this a little more elegant by reusing as much as we can. So I'm gonna save this guy, and then I'm gonna do save another one, and then I'm gonna do flare number 2. And then we can mess with this. Right, so what do we have? We have the color is different, and we have the scale. It's just the it's the initial setup that's different, right? So I don't know if I've ever done this, and I don't know if this actually supports this, but let's see if we can actually delete all of that. And then we plug that into here. No. Okay, so particle nodes, yeah, that's kind of what I feared. Like a particle update chain doesn't support splits and merges. I guess merging could technically be allowed, which is what we would want to do here, like this. But splits are not allowed because like that doesn't make any sense. Like what do you do if you split the execution of a particle? That's crazy talk. So we can't do that. Okay. So now if we play this, now we have broken the thing. Yeah. Oh no. Let's not do that. And now the preview died. It doesn't want to live anymore. Yeah, I know. No. Okay. Yep, self-made tools, ladies and gentlemen. I kind of suspected it would break though. Anyway, yeah, so we can do that. So what can we do? We can branch. We can branch on a condition. Oh, but we can't merge. Yeah, okay, so we can actually branch, but we can't merge. That's kind of annoying. So basically what I was thinking we would do is something like this, right? Where we have, you know, these three, those three nodes down there, and these three nodes up here. Right, like this, and then we do the initialization, you know, separately for these two guys, like this. And then we would need to go back to one of these particle updates. But the problem is that we can't do this. We can't connect these to both of these. because we don't support merges. At least not yet. So essentially what we could also do is every time we emit a particle, we would determine is this like the odd number of particle or the even. So if we kind of consider a running number from 0 to 1 to 2 to 3 and so on, every other one is going to be even and every other one is going to be odd. And then based on that, we could have just a single init flow like this. And then you know, we could select the color. We have a select node logic, right? Select by index. So we plug this into here, take the other color, plug this into here, then plug that into there, right? And then we would have a float node, math, float, float. We would have the same thing here, so plug that into there and that into there. The darker one has 5, the brighter one has 3, and then we plug that into there, right? Now the problem here is that what do we feed into these indices? I don't think the effect gives us any sort of ID for the particle or anything like that. Particle branch, yeah, that was that. Retrieve particle value. So this allows us to store data up to 16 floating point values per particle. So we have store particle value, we have 4 slots of 4 floats. Yep, that doesn't give us anything either. Emit particle, update particle. Yep, yep. Something that could be kind of useful would be like a running number node, which, you know, every time, you know, it would have an int output like this. They could plug into these guys, and each time you would get the value out of this pin, it would just give you a new value of a running number. That would be very handy. We don't have that though, and I'm always interested in figuring things out, how we can do new things with the set of nodes that we have. Update random int. Right, okay. Yeah. And of course, you know, it doesn't really make sense to add new nodes to this just to avoid a little bit of repetition. But it would be nice. I'm not gonna lie. Anyway, maybe we'll just go with this for now. This is a pretty nice way of doing this as well. We have red dark, we have red dark, we have red light. We share the same curve at least, so that's neat. And now, of course, with the normalized age and all of that, if we wanted, we could make these have like a longer lifetime. So if we set that to like 6, for example, the fade would still work. Like that, you can see the darker red kind of fading away much slower. Or the other way around, we make that 4 and we make that, put that back to 1.3. Now it's the brighter one that fades much slower. So the fades still work regardless of what we set the lifetimes to be. And it would be kind of tempting here. Like now we have native code generation. Would be pretty tempting here to add a lifetime here, because these are supposed to have the same lifetime, right? So. Yeah, now the lifetime is actually larger than the actual repeat time. But yeah, set that back to 1.3. And now it works again. And so this is nice because now we can adjust the lifetime from one place. However, now we don't have native code generation because no code gen method defined for the type sprinter nodes math flow node. So that's one thing that we could do if we wanted to in this stream. Well, let's have that as a last thing to implement if you want to have that. I'm going to get rid of that for now. So what we need to do now then is export this guy, which we can do by just clicking build effect here. Oh, and actually, I'm not going to use the red light flare 2. I did a little bit of cleanup on it there, so let's change that back to red light flare. Open that up and just click F7 and save it there in the same folder. So now we have a MRL effect and we have a bin MRL effect. So now then, let's put these next to each other, the new one and the old one in the level, and see if they look the same, basically. Refinery. And one kind of important difference between these two, and it's just basically how I have designed it, is that the old one starts automatically in the level editor, starts playing, as you can see here. With the new placed effect, I decided not to do that because we have these pretty large smoke pillars and things like that. Placed Merlin effect. And so it won't actually start playing. I'm gonna move it off to the side like so, and then do red light flare bin MRL effect. And let's click start right when that other one starts. I didn't quite manage to hit it. Stop. That's pretty good. I think that looks pretty damn samey. Now, of course, if we run the game, I'm not gonna save yet. If we run the game, they should basically be blinking at the exact same time, because the game starts them. As long as we have the auto start ticked here, we'll start them both when the actual level has loaded. Or actually when the game starts, which is technically a little bit later. So let's just fly over there and see. Here we have our two fancy little things. Oh, they don't actually blink at exactly the same time, but that's fine. Probably just something with the way that the objects are spawned at a slightly different time, and they start ticking at different times, if that is the case. Kind of looks like they are out of sync though, or is it just me? It's not necessarily a big problem, but yeah, it feels like they're kind of drifting a little bit from each other, right? Basically that the Merlin effect plays a little slower than the other one. I do know that the Merlin effects play in fixed time steps, while the old style particles play in variable time steps. That might have something to do with it, but I don't think it should really make them go out of sync. But it might actually. Yeah, I think it actually does. At least with the basic settings. The basic settings basically don't allow the fixed stepping to do any sort of catch up. Let's have a look here in the code. Merlin Manager. Is this still running? No, it's not. Let's see here. Where's the update? Here's update. Update instances. Okay, actually it allows doing 2 updates, okay. Yeah, you can see that this one is defined, this one is not. So we're advancing time by a fixed update, which is currently set to 1/60. Huh, that's interesting. Okay. And there's a typo. Typo to boot. Okay, well. That's neither here nor there. But it's an interesting thing to see. Maybe it's actually something funky with the old one. The Merlin effects have been used a lot more than the old ones, actually. And I believe there's actually like a hot value for updating those on a background thread, but yeah. Again, I don't know if that should really matter here. But anyway, I think it looks great. It looks basically exactly the same. So let us take that away. Copy the transform and move that there. There's our guy. Happily blinking away. We're gonna take another one, move it over here. copy that one, paste it there, and take that away. And we can start the effect. And it looks good. So we should basically be able to see here, if we go to render stats, there should be one more all style particle. Particles 2 actually. Huh. Particle system is there. Right? It's basically the exact same. If I delete that. All right. Okay, so it's buckets. Yeah, it uses 2 buckets for some reason. I don't know why. That's fine. And you can see that it uses one more non-indexed draw call every time it renders that. Yeah, I don't think they were. Maybe they were batched. I don't remember. Yeah, I don't know what this draw index business is telling me here. It just goes up and down. Anyway, so if we take that away, let's again copy one of these guys, or duplicate rather. So it would be this one. Let's move it to the top there. Duplicate. And then I think it's refinery. And is it mast, maybe? Yes, it's that one, radio mast. It has a particle system. Excellent. Can maybe rename that one and move it there. There we go. There's our guy. So now that we have several of these, do they actually stay in sync? Enjoy your error, says wishlisted. Thank you. This looks pretty cool, yo. What's going on right now? We are porting some of my particle systems from my old particle editor, which looks like this. I'm gonna lower the volume a little bit here. So the old particle system looks like this. It had a pretty... It was okay, but it had a pretty rigid sort of like workflow and only certain things that these particle effects could do. Porting them over to my new node-based thing, which looks like this. And so we created this blinking effect. This kind of red flare thingy in here. And I've gone ahead and replaced these blinky blinkers with the new effect. You can see that they're not actually in sync, which is something that makes me kind of happy, because it's been annoying me that they have all blinked in sync previously. Still might have to add some way to make it even more desynchronized. But yep, that's nice. And now we should not have any particles anywhere. Render stats. Which means that I can actually I can give some particle memory back, because the old particle system did some pretty silly pre-allocations. Well, it's 15 megs. I mean, it's kind of annoying when you know that it's not actually used for anything. But it's not that much. I remember it being more than 15 megs. But yeah, so the thing then that we could still do here is we could compile this into native code and have it running through that. Which again is not going to set the world on fire. These things are not very heavy. But still, it is nice to test that system out. We can look at the so let's I'm gonna export this guy now so we can run it without the editor. And then we can look at the profiler for these particle systems. And so now basically what happens is that we are running using a native Sprinter DLL. And that means that Merlin is going to run both native and interpreted node graphs at the same time. You can see that actually. Yeah, you can even see our particle systems being executed here in the interpreter. So we have these periods of a little bit of activity followed by periods of almost nothing. Of course, this is not like a whole lot. We're talking about 0.01 milliseconds here, and this is all of the interpreted effects in the scene. But I think it's basically just those three. Because first of all, this is so small that it doesn't really amount to anything really. And we can clearly see that it's the same pattern over and over again. Here's a little bit of a spike. Don't know what that is. Then we have the native side, which is this one here. I don't know what to call that. Is that like teal or something? Like light blue? So the teal plus this... Oh no, that is teal, isn't it? Anyway, this one and this one together form this Merlin effect instance advanced time. And this light blue one is the native side. And like you can see here, perhaps if we move this a little bit off to the side here, like this, and then we make this smaller. Window set size 720. 702. What? 720. There we go. Bloop. Move this off to the side. You can see a whole bunch of stuff happening here immediately when I start driving, because we're activating effects that don't normally do anything. Basis monitor has no cool name like the others. Yeah, the basis tools themselves don't really have names. I've explained this before actually. You know, you have basis monitor, which is this guy. You have basis editor, which is this guy. You have basis asset browser, and you have basis material editor, and you even have basis curve editor, this guy, and asset browser and all of that. Then you have these libraries that are not part of basis at all, like Nemo, which is this mission scripting system, and timbre, which is this audio tool, and then Merlin, which is this thing that we've looked at today. Yeah, I don't know if you consider the names cool or not, but yeah, they have distinct names, and I mean, yeah, I kind of like the names, obviously, since I chose them. But the reason why I don't have them be called, you know, particle effect editor and sound effect editor is that like it is too generic, because those things are like genuine like pieces of middleware, and in the game I have a lot of code that's like, you know, effect manager, or like, you know, sound effect this or that. And then if you have a very distinct name for your particle effect system, like Merlin, for example, if I see the Merlin name somewhere, I know that, oh, okay, yeah, it is that kind of effect. So the old system is just called particle effect, and it's part of the core engine. But if I had another system which was not part of the core engine, which was also, you know, called particle system, then whenever I see that in the code, I'm like, okay, so I don't know which one is this, and now I'm confused, and, you know, blah blah. So instead, for these, you know, middlewares that I create for myself, I tend to come up with a name that just like identifies that, okay, yeah, this is a Merlin particle effect, and it, like, the name of course has no meaning on anything. It is just there to identify this as being one of those things. Yeah, Goofy is the same thing, exactly. Yeah. Yeah, you have the UI, and of course you have there's a lot of UI stuff here that is not Goofy, and it's also not IMGUI, like these texts here, for example, or the command prompt. This thing is neither IMGUI nor Goofy. This is like the engine's built-in UI things. And so, for example, if I look for button, you can see, okay, we have basis UI button, and then we have Goofy UI button, and these are probably somewhat similar or ordeals. If we go down here, you have like UI button, which is a UI control, and then you have a UI button, which is a UI widget. But this is the Goofy one, and it's found in the Goofy namespace. So it just, you know, it, when you see this, you know that, okay, this is that and this is that. So there's like an actual like there's an actual reason for giving these things silly names. In addition to, you know, giving them a little bit more character, I guess. But that's kind of like not the main idea. It's not the main reason I do it. Okay then, I'm gonna go get a glass of water, and then when I come back, we're gonna start, you know, getting rid of this. Getting rid of these. Which should be pretty easy. We basically just need to add one more effect to our native Sprinter, or native Merlin library, rather. And when that happens, we should only see this native node graph update here. There should not be any Sprinter node graph update, because this is the interpreted one. These ones I'm sure we will see. Yeah. Yeah, this is the actual renderer, which is, you know, almost entirely taken up by this guy, I'm sure. But that's neither here nor there. Anyway, glass of water, be back in a second. Alrighty then. We are back. I started wondering here when I went away on my quest for water, what these particle pre-allocations actually are. And if we could just quite simply get rid of that stuff completely. You kind of don't want to necessarily you don't want to like mess with that system all that much, because that system is still in use and it's supposed to be supported still. It's, for example, it's used in the previous project slide. I'm just driving around here watching these stats. It's kind of interesting. Mesh instances 3,354. We have 1,906 meshes here. That's crazy. How have I added so many? There are quite a few runtime generated meshes though. That doesn't mean we have 1,900 handmade meshes in Blender or whatever. Terrains 2, cameras 1, point light 0, direction lights 1. Sky sphere and sunlight are both enabled. Yeah, mesh instance buckets. 14 out of 128. Yeah. Yeah, we even have some dispatches these days. I do the eye adaptation using compute shaders. I think if we spawn a mother here and we start messing around with the gravity crane, we're gonna see a few more dispatches, because yeah, now we have one more. These displacement effects are also compute shaders. Yeah, it goes down to 3 and then back up to 4. Okay. Cool. Anyway, let's start thinking about this a little bit. So, I don't need to save that now, thank you. Basically what we need here is this, and we need the resource path. That's easy. That would be this one, that one. The hash though is a little more gnarly. This is something I've been thinking of doing like for ages. I would need a handy way to actually hash a string. You know, like a tool that hashes a string for me. I don't know why I haven't done that. I haven't made that ever. But I have a lot of different ways I can do that, and I think the easiest one is quite simply just to add it. I don't know, here, for example. So we're gonna do basis string hash h. We're gonna do basis string make hash. That one. And then we're gonna print it. And that's a U32, so hash is %u, like so. Of course, I wouldn't be calculating these. That's the job of of the compilation system. Oh, I can do it there. Yeah, I don't have a debug console yet. I might not actually even have one there. Let's see. I'm gonna copy that stuff away. Just go to run. Yeah, it actually creates it here. Just throw it there. Thank you. Block this for a bit. Yeah, I think it actually probably creates it way before that, but it, yeah, there's our hash. Thank you. It just needs to minimize it there at the start of the run loop. So these are the two strings, or the two values that we need. That string and that hash. And now I can revert all of that. Thank you. So that would have to be. I don't exactly know where to create a tool that would do that for me. I mean, I know exactly how I would do it, but I don't exactly know what that tool would look like, which is why I haven't done it. Rightio. So we're gonna want to copy all of this. Copy. Let's put it in another file here, and then basically plug in these two values. That's that, and that's that. Maybe we can put on Zig syntax highlighting here. So the idea here is that you would see the code essentially like you see it here. Because if you have any warnings, well, if you have errors, then nothing is generated. But if you have warnings, then it would be nice to be able to see it. And then you can look at this code and go like, oh, okay, yeah, okay, yeah, generated that. But then the actual code that would be generated would have these things, you know, filled in automatically. Which, I mean, it's kind of silly that we have these things here. They could just be removed completely and start with node 0 there. That would be fine as well. Well, anyway, that would be that. So now we can close this down. And then we need to go into the correct workspace, which is this one, Sprinter Native. And I'm going to move my editor off here to the side so that I can cheat a little bit and look at these paths here while having full view of my main monitor. So this would be game underscore Merlin effects underscore miscellaneous red light flare .zig, right? That basically. Then we take all of this and we plonk it in here. Plonk it like it's hot. We don't want these things. We want some imports instead. Like that, right? And then we have this node graph store, which just has all of these things imported. So const node graph 6 is import. Then we have game red light flare. There we go. And now I basically need to just fill in this, right, everywhere. Let's just take this guy. Graph 6, or graph 6. And so here in Zig, we oh yeah, no, we want to be careful with this. Everything should be, you know, fully set up here correctly. And I could do some compile time magic to make this a little less fiddly to add in here, but you know, who has the time? And it's not really, doesn't really make sense to necessarily mess around with this, since this is all going to be generated anyway eventually. Maybe reasonably soon even. So node graph 6. Yes. Yes. Yep, that's it basically. Right, so here in Zig, we have our own version of a node graph. The node graph is found in, let's see, Sprinter source node graph. And you can see here that the node graph is actually a generic type. So node graph itself is a function which takes a kernel. And the kernel is the thing that like defines the node graph itself. The kernel describes all of the different nodes that are in the node graph, connects them together, and then kind of wraps them up in a type that has a certain interface. And then you can create a node graph of a given kernel using this function here. So it takes a kernel type and returns another type, if that makes sense. And then this is the runtime code for a node graph when it is compiled to native code. So it's basically exactly the same as the interpreted one. It's actually like eerily similar to the interpreted one. The only thing is that we take in this kernel here, which is a compile time known type, which means that we can like inline everything and make everything super fast and nice. And then here in the node graph store, when we create a node graph, we know the node graph type comes in here, effect type. And we look at, okay, is it this new node graph 6 resource path hash that we just set? Then we create a node graph with this create node graph internal function passing in the kernel type. So node graph 6.kernel. And then this guy takes that type and actually initializes a new node graph with it. That's how it works. And then we get a node graph which has the same interface to the outside world as any other, right? Even though it can contain completely different internal sets of nodes and all of that. To the outside world, it looks exactly the same. And the Merlin effect instance basically just calls start on it and then calls update on it as long as it is running, and that's how it works. So, pretty simple stuff actually, but there are a few layers to this onion, if you will. So now if we try to build this, what is going on? Not in the correct folder, that is what is going on. Build release fast. See if we can make this work. And this now spits out a new DLL for us, which has all of these node graphs sort of internally, and it also knows which ones it has. So when the Merlin runtime starts, it tries to load the DLL with the known name, essentially. And I need to copy that DLL because it is actually not copied currently. Where is it? Sprinter native. It's right here. Merlin native. Zig out. Binary. And here we go. So it's that one. 700 or 800 kilobytes. Let's copy all of that and put it next to the other ones. We are running a release. And yeah. So we're pasting the PDBs and the Merlin native DLL here. There's the game DLL. There's the core engine DLL. It just sits next to all of the other ones, and it tries to load Merlin native DLL if it can find it. If it can't find it, then it just gives up and goes like, okay, yeah, sure, we're gonna interpret all of the effects. If it can find it, it loads it, and then when a effect is created, let's see here, effect instance, I think it is. This has some sort of init function here. And we can look at this like node graph type, effect description, get native effect data. So it basically sets here, are we running this effect instance as a native one or not? I don't exactly know what this, remember what this does. Native effect type, I think this is actually the thing that determines if we have one or not, isn't it? Yes, exactly. So the effect description is actually the one that does it. So it asks the manager's native node graph data has effect node graph, right? And this is the thing that we looked at here in the Zig earlier. Has node graph. Has node graph is the name of the function, which I think is called from has effect node graph, which is exported from the DLL. Look at that. Has effect node graph is called here. Has effect node graph. So if we have a native version of this, then it stores the native effect type. This is the effect description. This just runs once for all the types, and then we have the actual instance. You can create like 100 instances of a single effect, and it just sets here, are we running native or not? Right? And here, if we are running is native, then we do this thing that we just looked at in the Zig code, create effect node graph. Find that. It's also exported right here. And then it does node graph store, create node graph, and now we go to the place where we just were. Unfortunately, I have to step out. No Man's Sky with my homies. That sounds excellent. Have a good No Man's Sky session. I'm probably gonna wrap this up soon anyway, because we're nearing the end here. I just want to see if this works now as a native one. Yeah, if we don't have a native node graph, then it actually goes and initializes the interpreted one. So node graph init with the node graph description. This node graph version here is the interpreted one. You can see here, interpreted or native. And the native node graph here has, you know, almost nothing, because all of the interesting stuff lives here on the Zig side. That's kind of how it works. So now then, if we now run this, let's make sure we boot into the correct level. Yes, we do. We can make the window a bit smaller, and we can also set the volume a bit down. And now if we go here to the monitor, start a new profile session, we should now see Merlin Manager update. Look at that, we only have native node graph things running. There is no more interpreted stuff. And here's what our native node graph now looks like. It looks pretty sweet, if you ask me. Yeah, we're not... I mean, it goes... spikes up above, but like the base sort of update time here for all of the native node graphs is sitting at like below a tenth of a millisecond, with almost everything going to this monster effect here, of course. Now if we drive around a little bit, we'll have a bit more life. I actually have kind of like annoyingly little debugging and profiling information here in you know, in the form of a debugging overlay or something like that in the game for Merlin effects. That's probably something I should do at some point as well. But yeah, that can come later, or basically whenever I need it. But yeah, that's pretty sweet. Now we're not running the old particle systems at all, at least in this level. So we're just like fully eliminating a certain systems update, essentially. For shits and giggles, we can have a look at the old particle system managers update and see what it is we are actually eliminating, because I don't remember anymore. It's been years since I looked at that stuff. But there are no particles, 0 buckets, 0 batches. Of course, there would be almost no batches. There would be basically a single batch, because the thing merges. But it needs to do like the merging and all of that at runtime, which is, you know, I mean, obviously it needs to do it because it's dynamic, but still, I remember the batching there not being necessarily super efficient, so it's kind of nice to just not have to actually run that at all. So as a last thing, let's do that. Let's look at what would it be? Is it maybe client CPP? And then I think it's called particle engine. Yeah, M particle engine. This guy. This is the old one, and it has an update, and that's basically it. It has a create and a destroy and an update. And this guy, update particle simulation, I think it's probably like if the thing is, if we are advancing time, yeah, so if we're not paused essentially, then we are updating the time. So it still goes here, but these should all just be 0. Number of particle systems waiting to stop is that, and here we just don't have anything, so we exit early. Yeah, and this is what I said about the threading earlier, that we do have actually these things running on multiple cores. So we're updating all the particle systems in different jobs on the job system. That's not something that Merlin does, but Merlin does things so much more efficiently that I'm not super worried about that currently. But in theory, we could run each node graph would be quite possible to run on its own job as well. Hey Jake, what's happening? What is happening? But yeah, now we're not even going there because we're not running any of these. We should not go here. We should go here though. Yeah. So I mean, the overhead of the old particle system now is basically a Boolean check and an integer check, and then a size call, and then a return. So that's nothing. So we're not even like poking at the job system there anymore. Which is good, because like if you can completely eliminate that, just probably comes with all kinds of benefits. Job system updates in you know themselves aren't a problem, but it's kind of annoying to have to poke at the job system just to update 3 flares. So now that we do it in essentially a call to a DLL, which does it in native code, that's very nice. Very cool. Right, so what do we have? This is the full Merlin update, 0.15 milliseconds or so, and that one is the advanced time, and then we have the particle renderer update and the billboard renderer. Right, so they're actually kind of flat currently. I was thinking it might depend on if I'm looking at those particles or not. This thing also, just like, it is super heavy because it has this massive smoke plume which like touches basically all the shadow cascades, and there's like a whole bunch of overlapping stuff here. So yeah, it's a bit of a monster in many ways. Anyway, that's that. Great fun. So, a little bit of an update before we end today's stream. Like I said at the beginning, I'm gonna be super busy for the next 4 or 5 or so days. So there's not gonna be any streams until next week at the earliest. But we'll see what happens. But basically, I won't have like a lot of time to work on this game over the weekend. Might have a little bit of time tomorrow. We'll see. But I am kind of in a place now where I'm thinking about which features do I still want to add to the next pre-alpha. So there's going to be a public demo at the end of summer. I've spoken about this on multiple occasions. And before that, I would like to put out a pre-alpha version for you guys, which you can access by going to the Discord. There is, of course, a link to the Discord in the description, as well as in the chat. And so if you want to play the game, you can already actually do so by going to the Discord and getting a Steam key for the playtest. It's a pretty old version, but it will be updated pretty soon And I'm kind of figuring out, okay, which features do I still want included in that. But yeah, I think we're nearing the sort of end of what makes sense to still stuff into that. Honestly, the pre-alpha is a really good spot right now. Thank you. It's pretty good. It's pretty good. I have a few more things that I want to get in there. I'm gonna get a drop of sound effects from one of my audio designers, which I still want to put into the game. Basically, I'm just waiting for the assets. Tutorializing, yes, indeed, and I have a plan for how to do that. I'm not sure if that is going to go into the pre-alpha though. That is going to go into the demo for sure. So the big thing in the demo is going to be voice acting, actual voice acting by humans, as well as better tutorials, and probably some fixes to things like option menus and things like that. You know, you might be able to rebind your keys and things like that. I think that's, for some reason, people seem to think that is very, very important. Not exactly sure why, but I'm happy to oblige if that makes people happy. And other than that, I think we are already in a pretty good spot, but there are a lot of things in the demo level that lack sound effects. So I think that's a little bit immersion breaking, maybe. Yeah, I mean, we already have an options menu. There isn't a whole lot of options in this, to be honest. I think video options is what most people want. There's not a whole lot of video options here currently. I've tried to, like, rather than giving a lot of options, I want to just optimize this well enough that it runs on almost everything. But yeah, input options would definitely be nice. I'm also lacking things like, you know, I just realized that the game is sitting there behind the chat, so that's a bit silly. I'm not even really doing anything. Finery. I'm also lacking things like controller vibration, for example. And there are... Actually, I wanted to go to the depot. There are other things as well, like the Unstuckifier UI. It's kind of rough. See, can I get stuck somewhere? Maybe on top of this rock or something. You know, like this. And then you have the Unstuckifier UI, which still just uses a debug text. Oh yeah, debinding or rebinding. Key rebinding should be fully supported already from the engine's point of view. It just needs UI work. So I've been kind of putting that off because I don't like UI work, to be honest. I'm toying with the idea of maybe even allowing for some gamepad rebinding, but I don't know, maybe we'll just have like a few options, a few different kind of setups or whatever you want to call them that have been, you know, tested and verified to work well. That could be an option. Yeah, I need to model this house. Please, yes, gamepad rebinding allows you to play with a much wider range of input devices. Yeah, I'm sure it does. Although I'm kind of thinking that there are probably some pretty good third-party tools for doing that these days, right? So if you want to play with some truly out-of-the-box input devices, I'm sure that you're going to be using something like that anyway. But yeah, it's probably a somewhat easy way to get player goodwill, just to have decent input rebinding. Yeah, like basically pause the game. I think my inputs are currently, they're not there. Where are they? Mappings. Input mappings is what it's called, actually. Yes. So yeah, I have a file like this, which is, you know, it's basically just a list of all the inputs, and I'm thinking like this could probably basically be turned into a JSON file or something, because it's basically just it's doing the same thing over and over. We have an app context. Like this is probably giving slightly too much power to the players, because they can quite easily break things as well. But you know, I tend to be kind of trusting on my players and and consider them pretty smart overall, because I'm exposing a whole lot of other debug functionality as well. But anyway, if you can expose these enums somehow to you know, like a JSON or YAML or whatever, like input IDs for the game, and these are things like free camera, yaw, pitch, elevation. We have some very game specific things like you know, crane, retract cable, extend cable, this sort of thing. And then we have the enums for the actual input devices. We have the keys, of course, all the keys that we support. We have the gamepad buttons, and we have, you know, mouse buttons, D-pad. Where's mouse? I have mouse here anywhere. It's probably just, yeah, it's here. It's probably input, isn't it? Mouse. Yeah, mouse x-axis relative, this sort of thing. So if I just expose all of this to like some user modifiable format, and then I just make the options menu actually modify that file, then I should be good to go. I'm not saying it's not a lot of work, it probably is. Probably takes like a week to do all of this properly, especially if you want to be able to localize the input actions and everything. But still, it's kind of already data driven. It just happens to be hard coded in this file. But there's a function to map all of this stuff. I just dump it to a JSON file, basically. Yeah, exactly. Exactly. So then, you know, if you comment that a little bit, make sure that people understand what those different values are, then first of all they can break the game completely by just, you know, by not mapping some of these things. The game is probably going to be completely broken, and so you might have to have some defaults or whatever. Because of course these things also affect what you show on the screen, right? If you play the game, let's see, what are our launch options here? Yeah, let's go into Depot, for example. You know, if you play the game here like this, and then we put down another vehicle here, let's put down a gripper truck. Right, and then you drive up to the gripper truck here. You can see that, okay, we have press Y to switch vehicle. So that Y actually comes directly from the input system. And so what happens if the user doesn't actually map anything to the switch vehicle button? Right? That's gonna be a problem. Or, you know, gripper arm. You can see all of those helper icons up there in the upper left corner. If I move my mouse, they're gonna switch over to like these guys. I'm gonna switch over to the keyboard, and then if I move the gamepad again, they're gonna switch over to the gamepad inputs. But anyway, the HUD kind of needs to know those things. You can't like not have a thing mapped to something. And so, you know, one solution is to have some default controls. Well, what if the user has mapped something else to that to that control? Then you kind of need to have a fallback. Well, what if someone has mapped something to the fallback? Well, then you have to have a secondary fallback. You know, it gets kind of complicated pretty quickly. So, but I mean, if it is like the 1% of the players who actually want to mess with that stuff, then I don't know, maybe you should just let them and tell them that if they break the game, then just delete the file and it will regenerate it. I think it's probably gonna be okay. So yeah, I mean, I understand why why a lot of games don't provide a whole lot of flexibility there, because it's a lot of work and it's, you know, it's time that could be spent somewhere else. But you know, I also feel it might make sense to just spend all the time and fix all of that stuff up. I haven't actually been here in this level for a while. It's nice to see that it does work properly, because like I said in the beginning of the stream, I've just been doing so many things on the renderer lately that everything could be broken, but nothing seems to be. How cool is that? Anyway, guys, I think I'm going to start calling it a night for tonight, because it is actually night here. Like I said, it's gonna be a few days kind of break from Traction Point work for me, and it will resume next week. I still have a few weeks of pretty intense work until I take a little bit of a summer break, during which time I have less time to work on this. But still, there's lots of stuff coming before that, including the new pre-alpha, which, you know, will be basically half a year's worth of work, because the previous pre-alpha was released in December, believe it or not. So it's going to be a pretty significant quality of life upgrade for everyone, I think, this thing. So yeah, look forward to that. And like I said previously, if you want to play right now, just join the Discord and you can get a Steam key, which of course will be updated with the new version. That's kind of like the whole point of using Steam already at this point, is that you can just join the pre-alpha playtest by joining Discord and just registering that key there. Then gives you access to the upcoming pre-alphas. I should also mention that you can already mod the game today. If you find that interesting, you can make things like the Flying Scout, which we've shown off many times on the stream. And the modding support will continue to be updated in coming pre-alphas as well. So lots of cool stuff to look forward to. But with that said, I thank you for your time today. Thank you for hanging out. Do remember to subscribe to the channel, both the live stream channel, which is this one, as well as the main channel. And you know, like, subscribe, tell your friends, all of that good stuff. See you next time.